Well, we'll get started with a prayer. The Lord be with you. Let us pray. Gracious and loving God, source of all that is, we give thanks for your created order as we seek to understand you more deeply through it. Guide our conversation today. Give us insight and clarity and wisdom. Help us to see your fingerprint on the beauty of this universe. All this we pray in Jesus' name. Amen. Well, we have a very exciting talk today. We had to reschedule it, so welcome, Richard. Richard Simon is an astronomer, and he is also a parishioner, and he's done talks like this before, and I think he'll have some slides for us, some images for us as well from the Webb telescope. So Richard, we are going to be talking today about the universe. We'll be talking about origins of the universe and what we know at this point. So why don't we start just with the big picture? What do we know about the origins of the universe? What don't we know from a scientific point of view?
From a scientific point, there are consistent theories, and there are always little holes or things that maybe don't quite work. But what we think we know about the universe is it started about 13.8 billion years ago. And the observations that led us to that conclusion also, and the theories that support it, lead to some very detailed predictions about things that we want to see in the most distant parts of the universe. And astronomers then have gone out and checked for some of those things, and some of them, like how galaxies and distant clusters of galaxies are formed, the way they're shaped, turned out to match these theories. So there's very powerful consistency between this broad idea of our universe starting with the Big Bang 13.8 billion years ago and what we see today. The telescope that I'm talking about, and the reason I talked about cosmic origins, is it allows us to peer and discover things as deep in the universe as we've ever seen before, except for what radio astronomers have done, which is something that goes beyond that in some ways. But to actually identify the earliest galaxies, a telescope is a wonderful thing. It's a time machine. The further out we look in space, the further back we're looking in time. So the Webb telescope is finding and discovering galaxies that formed only a few hundred million years after the Big Bang. So it's looking back in time more than 13 billion years. And right now there's a lot of excitement in the astronomy community because we're seeing things that are not exactly what we expected. And our universe has always surprised us, which is what makes astronomy an exciting subject.
Right. So, I mean, one of the big discoveries, right, in the 20th century was that the universe does have a beginning. Many physicists, my understanding is many physicists thought the universe might be eternal or everlasting, and there was never a start to it. But if we wind back the clock as best we can, right? How far can science take us back?
Well, we can actually see the dim glow of the Big Bang. You see that in radio astronomy. It's a glow. Everywhere you look in the universe is glowing at about 3 degrees Celsius above absolute zero. And this was discovered back in the 60s by some radio astronomers at Bell Labs. And they gave this very modestly titled paper that was only 1 page long. And they were eventually awarded a Nobel Prize for these observations because they were very careful experimentalists. And they said, there's something here and we don't know what it is. And so I think their paper was titled something that's going to sound really boring, an excess of radiation at 916 megacycles. If you're still awake after that, because what they did is they presented their observations without trying to explain it, but they'd also been in contact with theoreticians who very quickly realized what it was that they were seeing, which was a distinct echo. And this idea of an expanding universe, and one with a beginning, resolved a paradox that was first articulated by a philosopher and astronomer, Olbers, called Olbers' paradox. When we look, if the universe were constant and infinite in time and unchanging, when you look out, you see stars. But if it's unchanging, eventually you'll come to a star in every direction you look. So why does the night sky look dark? That tells you that the universe cannot be infinite and constant and unchanging. But it wasn't really until the 20th century that we understood that the universe is expanding, which helps, and that also it seems to have a finite beginning. So we do have a dark night sky to keep astronomers happy.
And it is the fabric itself of the universe, the space-time fabric that is expanding. It's not just that galaxies are moving farther apart from each other. It's the actual universe itself.
Well, as we've narrowed down our observations, what the observations are telling us, as we understand them today, so I always put these little caveats, is that the universe is infinite in extent, but it's also expanding. You can have infinities that expand, which is kind of, if you understand that, come to me afterwards to explain it to me. But, there are, just a side jump into mathematics, you can have countable infinities. The number of common numbers, 1, 2, 3, those are infinite. You can count, no matter how big a number you tell me, I can add 1 and make a bigger number. But there are also infinities that cannot be counted, like all the numbers between 1 and 2. There's an infinite number, and you can't count those. There's no easy way to count them. And our universe has some of those same properties. It's infinite, but it's finite in time, as far as we understand it. And there are a number of mysteries about the origin of the universe. The James Webb Telescope was specifically designed to probe much more deeply into the universe than optical telescopes. As you look further and further away in terms of galaxies and clusters of galaxies, things are moving more and more rapidly away from us. And it would look the same no matter where you were in the universe. It looks like we're at the center of an explosion and everything we see is moving away from us. And the people who are in some most distant galaxy would say the same thing.
Because there actually is no center to the universe.
Right, not that we've discovered.
Right.
And so the result of this is that we're looking in radio astronomy, we can see the dim glow of when the universe was a hot, dense, right after the Big Bang. And that's what we see at this super cold temperature, but it's everywhere.
So would it be fair to say that if we accept the Big Bang theory for the universe, that all matter and energy are concentrated into a kind of singularity, I think is the term that's often used, but it sort of an immeasurably beyond comprehension density, but we don't really know where that came from, right? Scientists don't have a theory.
That's right.
Okay.
And we can pose the question, what happened before the Big Bang?
So the Big Bang is just referring to the universe itself expanding.
The expansion of the universe.
But that concentration, where did that come from? We scientists don't know at this point.
That's right.
Okay.
And there's a number of scientific questions about the Big Bang.
Yeah.
And why is it that when we look out in that direction, we see exactly 2.7, whatever it is, degrees Kelvin.
Yeah.
And we look out in that direction, and we see the exact same temperature.
Right.
Very, very tiny and understood variations, to a part in 1,000, they're the same temperature. But that part of the universe cannot, we're looking at places that's taken the speed of light to get here.
Yeah.
And that part of the universe has never seen that, so how can they be the same temperature?
Right.
And there's some theories about that, but there's a lot of questions. First, people say maybe something happened that somehow violates the laws of physics as we know them, or requires new laws of physics. We don't know exactly what that is. People will talk about cosmic expansion. You probably heard that, and That's a shorthand way of saying that it appears that the universe was well mixed, everything's nice and equalized in temperature, and then it expanded faster than the speed of light somehow.
Right.
And then became this stately expansion that we see today.
Our best scientific theories can only take us so far at this point.
Yes.
We don't know how to reconcile these things in fundamental ways. So.
Yeah, and there's observations that can test those ideas.
Right.
And I am personally reminded of the situation around 125 years ago, when people were measuring the speed of light and trying to understand how is it that light can propagate through a vacuum. And there was a hypothesis some of you might have heard of called the ether. I'm sure you've heard of it.
Yeah.
And that was the idea that waves, in the ocean, waves are carried by water. And the idea was, can an electromagnetic wave propagate through the vacuum by itself, or is there something carrying the wave? And the something that was hypothesized was the ether, which somehow, in ways that nobody really could articulate, didn't interact with anything else in the universe, but it carried light waves. And so physicists began to make measurements to test that idea. One of the critical measurements, if we're moving through something that carries light, then we should be able to see if we're moving in one direction or another, the speed of light should change. And a very famous American physicist by the name of Michelson, I'm sure you've heard of him, a few of you have, did some very delicate measurements in the early part of the 20th century and showed that the speed of light, whether he had a giant optical table that was floating on a pool of mercury so he could turn it very delicately, and whatever direction he changed it, the speed of light wouldn't change, and the setup he had would have given it a signal. And it also didn't change with the time of year, depending on where the Earth was in its orbit. And these were pretty conclusive measurements that the simple idea of the ether was wrong. And it took a while, and Einstein to come along and say the speed of light is actually constant for everybody. And that has a lot of implications and a lot of weird things that happen that have all been borne out by experiment. But that's another.
That's a whole other topic. Well, now that we've got a framework about our universe and its origins and kind of what we know at this point, maybe it would make sense to see some images from the Webb telescope.
Yeah, and when I speak about the Webb telescope, this is something, the first proposals for it came out about 30 years ago. People, they actually had conceptual ideas of a telescope that would look something like this. And so this is an image of the Webb telescope. This is actually computer generated. But this is what it looks like out in space. And what you see is the gold area is the actual telescope mirror that reflects. Can you see? I forgot to make my mouse bigger. I was going to make it nice.
Just point to it.
Yeah, but the gold part is the mirror. There's a tripod thing. The light is reflected towards that tripod. And on the tripod is a subreflector, which then sends everything back to this black area in the middle. All the instruments of the telescope are actually located behind it, infrared detectors and imagers of various kinds. And this thing doesn't fit in any rockets that we had or one could imagine back 30 years ago. So the whole thing has to fold up. And right now it is flying approximately 1 million miles away from Earth in a place where the gravity of the sun and the Earth just about balance. So they can stay there with minimal fuel and they move the telescope around to point it at the various targets that scientists select. So I have a couple, and I want you to realize that this telescope represents, all the crazy things that are going on in the world. This also represents something that indicates the amazing things that human beings can accomplish when they work together. This was an international effort. It was largely an American design. The instruments are internationally produced. I don't know where they all come from. The telescope was launched on a European rocket. And this whole thing had to fold up. So this is just another image of it. So this is what the telescope looked like in the laboratory when they were still working on it. And what you see is those are people down in the corner. The telescope itself, the fully deployed telescope, would not quite fit into this room. The mirror is 21 feet across. And if you see where they're standing, the telescope would not fit in this room. It's an enormous telescope, 21 feet on the main mirror, and then it has something, the solar reflection, which we'll see in a moment, is designed to reflect all the energy of the sun away from the telescope, because this telescope has to operate only a few degrees above absolute zero, because it's working in the infrared. Otherwise, if the telescope was warm, the telescope itself would radiate into detectors and would completely swamp any signals we can see. So this is the telescope in the lab without its fully deployed sun shield. This is what it looks like, all folded up in its rocket. Here you see they have to fold back the side panels. Here's the main center section. There's another one of these on the other side. This is what they call the spacecraft bus, which has all the power and the solar panels and all of that. And so this is inside the shroud that was used to launch the rocket. And if I turn this on like this, this was the nail-biting moment for every astronomer around the world. So this is the launch from equatorial French Guiana. And so you see, and there it goes. So that's the last view from the Earth.
Rainforest to the edge of time itself, James Webb begins a voyage back to the birth of the universe.
And then this was the last view that we had of Webb after it was separated from the rocket. This is an actual video of the folded up telescope moving away from the spacecraft. And there you see it's all folded up. It has this kind of purple stuff to help control temperature. And there's a solar panel that they saw fold out, and that was it. Now, this is a video that shows you this complicated deployment process. This took several months. The telescope has to unfold. The first thing that you'll see is the solar panels come out. Any one of these deployment steps fail, and the telescope would not have been functional. So then you have to deploy the sun shield, which is this layer, 6 layers of very thin coated mylar. And the sun shield itself was protected during launch, so they have to uncover that. You'll see this part open up. There's a panel that's unfolded for helping control the heat. So you uncover the sunshade, which now has to fold out, and it was never tested in zero gravity. They tested it as best they could on Earth. They had some testing failures, sorted them out. And so this is what had to happen. It had to work perfectly. Not get tangled up, not get torn. And then they pop it up. By a week after launch, you can see all these multiple layers. Each layer is designed to reflect 99.9% of the sunlight away, so that all of this will stay super cold and not interfere with the observations. Now you see the primary mirror is folding out. Each one of these segments is independently controllable in piston, tip, and tilt. So they then spent several weeks aligning the telescope mirrors exactly. All the while, the telescope is taking some months to cool off and reach its final temperature. So the fact that worked without any flaws is a testament to the skill of hundreds and hundreds of engineers to design that, test it, and make everything work perfectly. Next. So this is an image that was taken by the Hubble Space Telescope, which was launched in 1989. And this is a very famous image that the Hubble took. It was christened the Pillars of Creation. Astronomers will know this as the Eagle Nebula because the head of the eagle, its claws, and these are the wings. But the reason it's called pillars of creation is that when you zoom in on it, what you actually see is a dense cloud of dust and gas that's being illuminated and eroded by very bright stars that are just out of this image. The super bright, hot stars with enormous amounts of ultraviolet light are able to light up the nebula around them and actually ionize the hydrogen and turn it into plasma. So you're slowly eroding these areas, but you'll see dense areas inside. So this was the view that we had with the Hubble Space Telescope, which was the best view of this nebula. This next image, where I'm fading the two together, is from the James Webb Space Telescope. In the infrared, where this image was taken, you can now see through the clouds of gas and dust, and you see tens of thousands of stars that were invisible in the visible light because of the gas and dust. And so now you'll see in areas, for those of you that are close enough, you can see these sort of arcs and so on. Each one of those is representing a star system that's forming. And so it's formed in a denser gas and dust. So as the erosion proceeds, these denser areas continue to hold their gas and dust with their own self-gravity. I think I zoomed in on this just so you can really get an idea. This is the Hubble image, and you'll see at the very tip of these some dark areas with stars right at the end. Those are very young, new stars that have been uncovered by this erosion process. And now when you look at it with the Hubble image of the same area, or with the James Webb image of the same area, you can see how you can see through this and see this is a nursery of stars. So today we're talking about the birth of stars. It is Mother's Day. I will personally thank all of the mothers here. And so this is one of the images that they released in the first batch of images that were publicly released. This is an area in the nebula Eta Carina, which is in a nearby dwarf galaxy down in the southern hemisphere. It's near the what's called the Small Magellanic Cloud. No, I'm sorry, I'm getting myself mixed up. One stop ahead. This is Eta Carina, and this nebula is named after a star that was very bright. It was around first magnitude, quite a bright star in the sky. And it gradually faded until now it's practically invisible. But the nebula itself is visible if you're in the southern hemisphere as kind of a hazy patch. You can see it by eye. If you take photographs of it, it's this beautiful nebula. They're looking at one small portion of it. And here you see the same phenomenon of hot, bright stars that are outside of this image are eroding away and created this erosion front. And they dubbed it cliffs, I think, cosmic cliffs. And here you see, if you zoom in on this, you can again see many of these same areas where now you see a couple of different phenomena. One is you'll see things like this, where there's a dense cloud here. And so the gravity of a new star system is holding that dense cloud, but the outer edges of it are being eroded away by the super hot ultraviolet stars. But you also see things like this, where there are, when a star forms, it'll form a disk, and it'll eject material along the axis of that disk. And this is well known. As material spirals in, it's carrying a lot of angular momentum, and magnetic fields get all twisted up, and in ways that are not completely understood. Things that are accreting matter like this will send out jets along their axis. And it's very common on all the scales, from baby stars that are forming all the way up to massive black holes that are forming. So this is another image of a very young star system. And if you can see, there's a small line here. So the star system is forming a disk that is at a vertical angle like this. And so that part is very dense with dust, and even James Webb can't see all the way through it. But at the poles, north and south poles, it's the disk isn't so thick, and so the new star is illuminating that and also sending out material, and that's what you see here. So it's called the butterfly nebula, but what you see is there's more gas and dust on this side, so it has a bit oranger, and this side's a bit blue. But you're seeing material that's being ejected from this forming star system. The star is collecting material, but at the same time pushing out material, and it's no doubt forming planets. Now I'm going to move to a system that's a little bit further away. This is the one I mentioned, or started to get myself confused about. This is a star cluster in the Small Magellanic Cloud. And here you see tens of thousands of new stars that have formed, and the gas and the dust around them that is left over. And so this nebula is actually called the Tarantula Nebula, and this is a small section of it. The Tarantula Nebula itself, or the Small Magellanic Cloud, are visible to the naked eye if you're in the southern hemisphere in a reasonably dark place. As some of you know, I worked for many years in Chile, and when I had the chance, I would go out and look at the stars at night. When you're in the big city in Santiago, you're not going to see the Small Magellanic Cloud, but when you're in the mountains, it's very easy to see. And this is one nebula in the Small Magellanic Cloud, which is has formed thousands of stars in this star cluster. And they're lighting up this nebula and pushing away the remnants of the gas and dust. Now, James Webb is able to see, and this is another star. This is a large star. This particular kind of star is called a Wolf-Rayet star, and it's named after the astronomers who first identified it. This is an extremely massive star that's at a relatively late stage of its cosmic life. Massive stars burn through their material extremely fast. A star like our sun takes about 10 billion years to use up all its nuclear fuel to turn hydrogen into helium and heavier elements. A star like this, instead of lasting 10 billion years, might only last a few million years, because the bigger star not only shines brighter because it's bigger, but it's burning everything much faster. Towards the end of their life, the inside part of the star gets so hot that it starts to drive off the outer layers. And so here you see the outer layers of this star have been driven off. This is actually about 10 light years across, which is 60 quadrillion miles. If that means anything to you. And the point is that this star is driving off its outer layers even as it's furiously burning even more rapidly the stuff on the inside. And a star like this is likely to go supernova at some point in time. Probably not quite yet. This is another example of a star driving off material. Star systems are very complicated because of the materials that are in the stars, how much hydrogen they have versus heavier elements. They can also be complicated that most stars are found in binary systems. That means one star is orbiting around another. And it might be a nice circular orbit, or it might be an orbit where one star dips in close, and back out, spends most of its time far away, and then dips back in again. And so in this case, every time one of the stars is shedding material, but every time it gets in close to its companion, the companion star itself is also hot. That heats up the star, it drives off even more material, so you get an extra pulse of material coming out. And then it goes back out and it comes in again. So these lines that you see, and there's like 17 of them, are actually each pass of one star past the other, generates another burst of material. And before James Webb, we could see 3 or 4 of these lines. Now we can see them all the way out. And this is material. People have built actual detailed models that show why it has the shape that it has. But it's just, we live in an incredibly dynamic and changing universe. When I go out at night and look at constellations of stars, I love doing that. That's what got me into this business, I think. I see the same thing you do. I see constellations that don't appear to change. But in fact, as you start studying stars, they evolve and change with time. Some, fortunately for us, the sun, change fairly slowly. Others can change very rapidly. When stars reach the end of their lifetime, especially more massive stars, they will explode in a phenomenon called a supernova. And in there's various causes of the supernova, but basically what happens is that the core of the star has consumed all of its fuel. It can no longer support itself. The core collapses and it bounces and releases an incredible amount of energy. Most of it comes out as subatomic particles called neutrinos. 1% comes out as light, and we'll see these brilliant stars light up. They will outshine an entire galaxy. And there was a lot of excitement. The closest one we've seen in modern times was in 1987, and it was in a relatively nearby galaxy. And one star that was generating some excitement, if you remember a couple of years ago, people were talking about the star Betelgeuse. It's a red giant that's in Orion. You can see it easily in the wintertime. And Betelgeuse dimmed by a factor of more than 2, and which was really something. People say, is it going to do something? And what we think we know about Betelgeuse is sometime in the next 10,000 years, whether it's 10 minutes from now or 10,000 years from now, these are kind of the same to an astronomer. Betelgeuse will become a supernova. We're safe here, we're 500 light years away, but it'll be very bright. It'll be much brighter than the full moon, and it'll be this brilliant, easily seen spark in the sky, even during daytime. And it'll shine for several, possibly several months. But we don't know when that's going to happen. This particular star is called Cassiopeia A. It's the brightest radio source in the sky, and it also forms a nebula. What you're seeing and what's new with the James Webb telescope, which isn't completely understood, is all of this material in here that you see in green. This is actually a montage of several images, and the colors are related to, the orange is dust, and the white areas are ionized material where the atoms have been stripped of their electrons. And there's some very energetic material that you see here in green. And this is actually a swirling, dynamic nebula. You can actually see over the last couple of decades, you can see it expanding. We know that it's expanding. At the radio, when you measure it, its radio radiation is still fading. This exploded, I'm trying to remember, some 1,500 years ago, if I'm remembering the right number, but it wasn't observed or cataloged from Earth that we know of, possibly because there was a lot of obscuring gas and dust, so it wasn't especially bright. Now, before we move on, there's one thing which they haven't released it yet, but there is another famous nebula called the Crab Nebula. And I saw a talk just a couple days ago, but they haven't released the images of the Crab Nebula. And that one exploded in the year 1054, and it was recorded by astronomers in China. It wasn't noted in Europe. Maybe when it exploded, it was wintertime and the weather wasn't good, and people just didn't notice it. But it was noted as a guest star by the Chinese records. So we actually know the date that star exploded. Now, 1,000 years later, it's this big, complicated, swirling mass, somewhat similar to this, but with different phenomena. And astronomers can look at everything from radio, infrared, visible, X-ray, and actually start to determine how big the star was and what it might have been like. Was it part of a binary companion? How much mass? So now I'm going to move to something closer to our cosmic origins. And one of the things that James Webb can do is look back in time and see galaxies. And so this is a deep image, and everything you see on this image, virtually everything, is a galaxy. And some of the things you see, one of the most noticeable things here are these funny streaks. And those are actually caused by this foreground galaxy is distorting and magnifying background galaxies, much like a natural lens, and it's a gravitational lens. And in this case, this is another cluster of galaxies that's a gravitational lens. And then they've looked at some of these most tiny distant spots. It turns out that those three things that are in are actually three images of the same distant galaxy that have been magnified, because it's an irregular lens. And just like if you put an irregular lens by a candle, you'll get different spots on the wall. Well, that's what we see here. And the thing that I found really interesting is not only is James Webb looking back in time to, this galaxy was probably only a few 100 million years old to a billion years old, not the 13 billion that we have today. And there are three images, and they can model the gravitational field of the foreground cluster. And if you can build a model from the images that you can see, you can determine that these three images, these little squares, are all images of the same galaxy, this galaxy right here. And in this image, and there's a foreground star in this part of the thing. But what you see here is that this is one image. This image is actually delayed by 320 days. This one's 1,000 days. So the images travel different distances through the lens. And so we're actually seeing three different snapshots in time separated by 3 years of the same thing. And as it happens, there was a supernova that's not visible here or here. And so not only is it a time machine looking into the most distant universe, but these gravitational lenses can let us see the same galaxy at different times spaced by several years, because the light has to bend and follow a different path. And I found this amazing. I didn't realize that they actually got that much of a time delay. This is another very deep image, and here you see these little faint red spots that you can barely see. And these are blow-up images of it. And these are some of the most distant galaxies that we can find. They're magnified by a cluster that's this cluster down here. And those images are magnified. So astronomers can use medium distant galaxy clusters, and their gravity will magnify things that are even further away. So we can see, and you have to do some complicated math to try to figure out what the galaxies really look like. So these are all candidates for extremely distant galaxies. And this image was one of the images that was first released by the James Webb. They took, for this image, this was a 12-hour exposure. So they pointed the telescope at the same section of sky for 12 hours and let the photons build up in the detectors. And what you see, again, is the way that we can explore the deepest universe with a foreground galaxy cluster. And all of these streaks that you see all the way around the image are background galaxies whose images have been magnified and distorted by the foreground galaxy. I should also add one thing that you see, where you see these bright objects with the big 6 flares or 8 flares coming from them. Those are probably foreground stars. They're relatively bright. And the 3-legged tripod and the hexagonal mirrors on the telescope create these diffraction patterns and other things that are very bright. So I think I have some more things, but I think that's a good place to start.
Well, let's transition to some questions, but maybe just do a quick summary of what we know. So we know we're in a universe that's roughly 13.8 billion years old, that it started with some sort of intense concentration. We know that this universe is dynamic, that galaxies and stars are constantly changing, interacting in a variety of ways. There seem to be laws that govern these interactions that can be explained in mathematical language, which itself is a kind of strange phenomenon. Why is that the case? And so we find ourselves in a very sort of dynamic, interesting, complicated universe where we have a fractional understanding, if you will, of what's going on. Is that a fair summary?
Yeah, I think, and many scientists have remarked on the fact that the amazing thing is that as far as we know, if we work at it, and it can be a lot of work by a lot of people, we are actually able to understand this universe. We haven't run into something that's so mysterious on the physical level that we say we can't understand it. It's just, if we don't understand, we just need to collect more information with better telescopes or more careful observations to try to understand what we see and explain it in terms of the basic physical laws that we know. But there are hints of things that we don't understand, and that's what makes science exciting.
The remarkable thing that I think what you're saying is that we can actually understand it, right?
Yes.
We're this species on one planet, right, in one solar system, in one galaxy, but we can understand this vast universe in ways that's pretty remarkable because it has this intelligibility to it, and our brains are able to understand it. What questions do you have for Richard? Yeah, Paul, back.
Richard, does the universe have any boundaries?
Boundaries to the universe.
From what I've read about Stephen Hawking's belief toward the end of his life is that he came to the conclusion that there were no boundaries in the universe.
Well, the universe, you've heard of, we're all familiar with 3 dimensions. We live in a 3-dimensional space, length, width, and height, X, Y, and Z. But there's another dimension that's very important to all of us that we are all moving through, and that's time. And it's a little tricky to talk about the universe being 13.8 billion years old. The way you arrive at that number is you say, all right, what if we take all the measured motions of galaxies and just reverse them? When would they all have started out? Or when the gas and dust that formed them, that's where you get the 13.8 billion years. Now, the idea of what time is, and this is not something I can speak with any authority on, but time is the way we measure time is we find a regular phenomena in nature. A ticking clock, the pendulum goes back and forth with a known rate. Or our time these days is defined by molecular or atomic transitions. The transition of cesium goes so many hundreds of billions of times per second, and cesium atoms are the same everywhere. So we're measuring time by the vibration of atoms. But how do you measure time before atoms existed, when you had the earliest part of the Big Bang? So time is a slippery concept, but it seems like our universe is finite in time as we measure it, even though it's infinite in space.
Interesting. Yes, sir.
So Richard, all this stuff is so far above my pay grade that I didn't even know you can make your mouse bigger.
I apologize for that. I'll show you how afterwards.
Now that I know, you need to teach me. So is the universe science and is creation religion?
I would say what scientists do and what we try to do, and scientists are human beings, so they don't do it perfectly, is try to observe what's there and understand what it means. And especially in astronomy and physics, you try to if you observe and understand something, you can break it down into mathematical laws that describe what we see. And you've all heard of Isaac Newton, who formulated Newtonian mechanics and explained why planets move around the sun. But it just says that there's gravity, which is associated with mass, and it has certain behavior that lets things orbit around other things. And Einstein went further than that because there were some small deviations from Newtonian mechanics. And they had to do with the interaction between the speed of light And Einstein formulated gravity as a bending of space and time by mass. So that, and you've seen these pictures of, a heavy weight sitting in the middle of a drum or something like that, which is a very nice visual representation. But again, we can use a mathematical representation to explain, these galaxies that are being distorted and bent. Einstein predicted that gravity would cause light to bend. It was first measured by minor bending around the sun during a solar eclipse, and now we see it as a very common phenomenon around distant targets. And
following up on Eric's question, could we say perhaps, so scientists are able to mathematically explain how matter and energy are interacting, and they come up with various theoretical frameworks for that explanation. The idea of matter and energy warping time-space is a even better theory than Newtonian mechanics to explain what people observe. But why there is something to begin with, why the universe makes sense mathematically, where that singularity came from at the beginning, those are, in a sense, not scientific questions, or at least not known or accessible to scientists at this point. Why is there something rather than nothing, for instance?
And the thing that's it, we live in this amazing universe, and we can, something like the James Webb is studying it and revealing details of that universe. And there's a lot of excitement right now because there's hints in the data, not confirmation, that galaxies are a lot bigger and more complicated in these early eras than anybody expected. The idea was sort of to confirm or see what's there. So science is trying to see what's there. But on the other hand, we live in a universe that gives rise and has the existence of love. And that's something I've certainly experienced, and I imagine we all have, and yet you can't give a mathematical explanation of love.
Yeah, that's true.
And so
there's a whole value dimension to reality that is just outside the realm of science. Yeah, go ahead.
I'm going to fire 3 questions at you. One is, if my grandson asked me what a galaxy is, I'm not sure that I could identify it. The second question is, with the Webb telescope, what is the life expectancy of it, and is there another telescope being developed that's even stronger? And the last is, I've been to Greenback, which I highly endorse anybody that has not been to Greenback, West Virginia, is how does that radio telescope work? I'm sure it's not as good as the Webb, but it's just so mammoth. I've never clearly understood it.
All right, so these will have to be our final 3 questions. So,
all right, let's see. I'll take them in reverse order and see if I can remember all of them. In Greenbank, for those of you who aren't familiar, there is a 100-meter diameter radio telescope. It is the largest fully steerable radio telescope on the planet. And the way it works is much the same way a small satellite dish works. It has a surface which is larger than a football field, but it's in the shape of a parabola. Radio waves fall on that and are reflected. Parabolas have this nice property that they will focus light to a point if it's from a distant point. And so at the focus of that telescope, you mount electronics to collect these data. And it's much like having a radio or a television receiver, but they have to be specially designed to be as sensitive and not introduce their own noise. So that's the 30-second summary of how it works. And let's see, the second question was how long will James Webb last? The launch that you saw actually went extremely well. The rockets, there's always a little bit of error in how rockets exactly burn, because they're pretty complicated explosive systems. But the rocket burn went extremely well. The burns to get it into orbit worked exactly. And so the original design was to have 5-year mission with hopefully enough fuel for 10. Things went extremely well, and the estimate now is that it will last about 20 years before they run out of the fuel that they need to keep pointing the telescope to its various targets. And then the first question was...
Now, Is there a follow-up?
I know that people are thinking about these follow-ups. I'm not involved in any of those efforts. One of the things that I just saw a comment somewhere, people are very excited about some of the new generation of extremely large rockets. If it works, this giant SpaceX rocket would have let you launch something like the Webb, but without having to fold it up. You know, the volume inside of that is 9 meters across or something like that. So you could launch something the size of this room or something like that, the size of
So when my grandson asks me what a galaxy is.
What is a galaxy for a grandson?
a galaxy is a swirling concentration of typically trillions of stars that are, and you see galaxies in a lot of different shapes. They can be blobby amorphous things, those are called elliptical galaxies, or they can be these beautiful spiral galaxies that you're familiar with, where the stars are mostly rotating in a pancake-like plane, maybe with a central concentration. That latter is the kind of galaxy that we live in. And all the stars, when we look at night that we see, are members of our own galaxy. And you can measure their motions and make determinations about them. You know, here's a picture of our galaxy.
Oh, there you go.
And this is in the southern hemisphere, and it has, you know, the star circled in the center is Alpha Centauri, which is our closest star. But you see this incredible cloud of stars, that's the Milky Way. And, you know, all the stars that you see, and I wouldn't want to have to count, these are more stars than you can see by eye. This is a photographic imagery. It's just looked much deeper.
Well, thank you so much, Richard, for sharing this with us, and I'm sure he'll be around to chat with you more about other questions.
We have one more question.
Yeah, just one last practical measure for a real game. If we were to, and it's a two-part question, if we were to say that Earth is, let's say, Newport News, and we're looking west, how far would the Hubble extend the field of view for us from Newport News? Would it be roughly Charlottesville? Let's say Charlottesville. And how much further would the James Webb extend our view west? And then the follow-up question is, how much larger is the universe than the known universe we can see with James Webb? Is there any way to determine that?
Okay.
We're going to have to wait on that. I'm sorry. We're at the end of our time. So we'll have to answer that after the... Let's give Richard a round of applause. Go in peace to love and serve the Lord. Thanks, Richard. Thank you.